Okay, very good. So welcome. Happy New Year, everybody. I hope you had a good break. Those of you who are new, and we have, I think, maybe two new faces that are going to join the class. So welcome, Khalid, for example. Uh, and then some of you are who are not new to the campus, like Mariam, but you are new to my class. So welcome to you as well. And uh, I like to believe that I do things slightly differently, but you will see how different they are compared to other classes. Again, this is E&M. It's one of the most difficult classes you will take at Western, and it's difficult not because I want to make it difficult. It's because the subject itself is difficult. It's the most complete theory there is. So it's the most complete and most successful theory in physics is classical electrodynamics. So we'll just kind of set the stage for the study today. It is highly mathematical. The goal of this class is also to introduce you to the mathematical techniques. So that's going to be our focus mainly. So we will uh, work through quite a few of the theory foundations, the conceptual foundations, as well as the mathematical techniques. And so those of you who were not in the math methods class last semester, you will have to do some extra work to get up to speed on math methods. And I will point out when the time is right, which methods you need to be familiar with. And you can talk to so this is especially true for Khalid, Mariam, Juan, and Malik. When I point out, and even Thomas, when I point out a specific technique that we're going to use, if you're not familiar with it, you can ask your other fellow classmates for lecture notes on that topic or something like that we have discussed in the math physics class last semester. And I am going to be relying heavily on some of the work that we did there so that we can go deeper into the set of topics that we're going to study. Okay, so make sure you understand that there is going to be certain effort required from your side to bridge the conceptual gaps that you may have. Those of you who are in the 420 E&M class as a deficiency, take that class seriously. Some of the mathematical ideas that we will use, you will get introduced to them in that class, though the way we will do things in terms of the notation, in terms of the depth of the mathematical techniques and the conceptual depth, it will be very different from that class. And that's true for all of the master's level classes. You learn these things, I'm sure all of you had a very first college level class, maybe second, on E&M. The way we do E&M at the 200 level is very different from how we do it at 400 level, and then it's very different from how we do it at graduate level. And so make sure you sort of understand that the conceptual depth and the philosophical depth changes quite a bit, and so you need to be sort of mindful of that. So what we will do now is let's just quickly go over the syllabus, and then we will start the discussion of some of the initial concepts. So I'm sharing my screen with you, and I need to find where the syllabus is. So, okay, so you can see the syllabus right now. All right, so I say classroom currents 205, but we will do this via live stream. It's just much easier that way. I don't enjoy teaching through a mask, and if you are not masked in your in your private area, then I can see your faces. So that's going to be important thing. If you're not showing faces, you want to change that. Stay fresh. This is a first class in the morning, so I understand some of you may have to get adjusted to your sleep, new sleeping schedule. But do that. You need to show your faces, not just a picture or not just your name, right? So I'm checking up on you, those of you who are not showing faces yet. You need to show your faces so I can get some sort of a visual feedback on whether what I'm talking about is making sense or not. And remember, the class is not for me. I don't have any agenda as to how much I need to cover in this class. It's up to you. You want to be comfortable with the material, so stop me at any point. Wait for me to complete a sentence and then stop me, and I will be happy to go over things or talk about things in more detail or talk about things slightly differently. Go even deeper into the concepts if you would like that, right? So it's up to you. Make the class your own and make sure you follow everything. Okay, so I'm still waiting for faces to appear. There we go. It doesn't matter how you're, if you're in your jacket or wearing hats or just woke up, it's fine. But you need to show your faces. Okay, so that's the class link is not on here, right? But you have a calendar invitation. If you haven't gotten used to using Google Calendar, please do that. Very good resource. I live on my calendar, through my calendar. It's very difficult. I have half a dozen meetings every day, and so the best way to keep track of them and not forget is use the Google Calendar. If you have a smartphone, mine you cannot see. Okay, there you can put Google Calendar app on here, and so then it will send you notifications. I'm sure all of you have smartphones, so do that. My office is Karan's Hall 300, but most of the time I will be seen in the chair's office downstairs in Karan's Hall 2 and 2. If you set up an appointment, and these are my office hours, Tuesday, Thursday 2 to 3, Friday 10 to noon. But again, I serve as the chair of the department, so sometimes I may get called on at those times for meetings and such. There are several committees on campus that I'm part of, and so it's best to check with me if you want to meet. So that's why the phrase here, pre-arranged meetings via email. Just check with me, I'm there, and then I can send you a Zoom link, or you can just come downstairs in person and then we can chat. So either way is fine. During the class time on Tuesdays and Thursdays, I'm teaching from home because it's just a lot more convenient. But then immediately after this is done, by around 9:45 or so, I will be in the physics office. So if you need to see me there. So that's how those things are going to work. So let's take a look at this motivation behind this class. For me, that's sort of my personal goals, but it doesn't have to be your goals. And if there is a conflict between those, your goals are important. So you want to feel comfortable with this material, right? At the end of it, the idea is that you feel comfortable with the material. And let me just point out to you the textbook we will be using for the class. So the textbook, I say here, the Modern Electrodynamics, Andrew Zangwill. It's a newer book, so this is how it looks. Modern Electrodynamics by Zangwill. It's a relatively recent book. I think we are still using probably the first edition, or maybe a second edition. Let me just quickly check. Yeah, it does not even say which edition. So it is a first edition. It was first published in 2013. So it's a very, very recent book. And the nice thing about it is it covers all the basics that you need. So if you want to use it for some of your, to develop understanding of some of your 420 material, you can do that, but it goes deeper, and it also looks at some of the modern methods that are used in classical electrodynamics research and that are motivated from research, some of the teaching techniques. So in that sense, it's very good. But of course, the classic J.D. Jackson is also very useful. If you are not familiar with it, you may want to get that book as well. The trouble with Jackson is very difficult to read, right? It is written as a research paper with one, lots of conceptual and even mathematical gaps when you go from one equation to the next. And just to kind of avoid that and provide you a solid resource, I have chosen Zangwill's book. So make sure you look at that. Zangwill is from Georgia Tech. And one of our alumni is actually working at Georgia Tech. So just to kind of give you an idea. Anyway, so that's the book, but you can have Jackson as a resource along with you as well. I will be following things from the book. I will give you maybe some reading assignments here and there. So it's good to get access to the book. Problems that I assign, they are a mixture of problems that come from Jackson, from Griffiths, and which is undergraduate level textbook, and Zangwill. But Griffiths has some very nice higher level problems that are in the undergraduate level textbooks, are not, but only meant for advanced students. And so I can use some of, I use some of those as well. So it's a mixture of all three, and small variations on those. I don't exactly use the problems word by word for the homeworks. Okay, so let's take a look at the motivation behind the class. Again, like I said, the classical electrodynamic theory is the most successful theory of the electric and magnetic fields and generation of those and so on, their propagation through space and all of those. And it's the let's just read through this. It's an important part of the core understanding of theory physics necessary for graduate students. Now, and that's why it is part of the core for the master's program. Even if you are going to study experimental physics, right, later on, or if you're going to do electronics, or if you're going to go into electrical engineering, or if you're going to do astronomy, you can't escape not knowing the concept of E&M. You need them. They are crucial. And so this is the idea. Again, unfortunately, though, we don't have a second part of the course to really develop full-fledged understanding of E&M. You need second part of the book. So like for example, we will be able to cover only first half of the book if we get to all of that. The second half of the book talks about the propagation of E&M fields, how they are generated, like the oscillatory dipoles and such. And those ideas are extremely crucial if you're, if you want to study how the communication networks, the cell phone communication networks work, or how do you build a radio telescope, for example, to be able to intercept the signals from outer space and all of those ideas, or even at the microscopic level, how is light itself generated? You need sort of the second part, the relativistic theory of classical electrodynamics. So relativity and E&M combined together, and then field propagation. Those are the ideas that are missing from this class. That's part of the second, normally a second class, but you do get a flavor of that if you take 421G with Dr. Babu. I think it will be offered next semester in the spring. No, this is spring, in the fall. And so if you get a chance, those of you who are not graduating, then you can take that. And there you will get some flavor of connection between relativity and E&M. But it uses this, it relies on the second part of Griffiths, not so much the graduate level work, because it's a mixed graduate and undergraduate class. But that's just the reality of where we are here in the department. So it's one of the most successful theory of physics, and is a precursor to quantum field theories. All of the high energy physics, study of subatomic particles is done through quantum field theories. In fact, even condensed matter physics, solid state physics, modern methods in solid state physics uses mean field theories or quantum field theories. And so this is a precursor to field theory. You will understand what a field theory is. What do we mean by fields? How do you deal with them? How do you handle them? And some of the methods are also analogous to fluid dynamics. For example, Now in physics, the standard core physics knowledge, we don't really focus so much on fluid dynamics. It is mostly covered in the mechanical engineering, civil engineering curriculum these days. But there is a tremendous amount of parallel between a fluid flow and the field flux and so on. So there are quite a few concepts that are similar in E&M and fluid dynamics, if you will. There are several active areas of research resting on the foundations of E&M theory. So it's not, even though it's classical, it's not old, it's not dead. It's a very active field of research. You need the understanding for a variety of different areas, such as photonic crystals. These are periodic structures of materials with different refractive indices, right? So you have let's say glass material, but then some other material in between, or you can make actually glass and air type matrices, things that have holes in them, type structures, and these structures are then periodic in space, just like a crystal, crystal made out of atoms is. And those periodicities give rise to very interesting properties for the electromagnetic waves. You can actually trap light into these materials. You can amplify it. You can do lots of cool things. You can actually even change, as a result, an extreme case of these photonic crystals or these periodic media is the next item here, phenomena of negative refraction. You can manipulate the effective refractive index of materials by creating these interesting periodic structures. And then comes my field of physics, quantum optics, which deals with light matter interaction, how light is generated, how you can use the light matter interaction to manipulate both the properties of atoms as well as light. And the field of quantum optics now has found applications into a very, very applied and very exciting area of information. All of the quantum information hardware uses techniques from quantum optics, even though they may not directly deal with atoms, but they have atom-like entities which have discrete energy spectrum interacting with light. And so that's those are sort of the foundations for quantum information are coming from, part of the foundation, the experimental stuff comes from quantum optics. The software and stuff comes from information theory. So it's a very interesting mixture of quantum optics and information theory. Biophysics, of course, you may think, where is electricity in biological system? We don't work. If there was no electricity inside our bodies, we would not work, right? All of the signaling, when you hear me, it's that information through your ears is going through your brain. All of that happens through some sort of a signaling mechanism, which is electrical, right? And so our cells have this capability to deal with electrical signals, make sense of them, and so on. And this is not just some specific neuron related cell or the neural cells, but it also applies to any ordinary cell. There are these ion channels that cell membranes have. They are used for the cell to communicate with the outside environment. And so that communication or transfer of materials from the inside of the cell to the outside happens through the cell membrane through something called ion channels. So it's all electromagnetic phenomena. And then, of course, radiation physics, which has tremendous amount of applications in variety of different areas. Some very applied, like the cell phone companies needing to know how radiation propagates and how to effectively cover, let's say, you want to have 5G signal in Macomb. Right now we don't, right? And so what would you have to do? How many towers would you need? Where would they have to be situated so that every building, every house in the city has the 5G access, right? So that's a difficult problem to solve if you look at it from fundamental principles, but of course some of the groundwork has been done. So engineers now have sort of ballpark theorems or ideas that you build out of this fundamental theory, and then you just use use those for applications. All of astronomy is essentially radiation physics. That's how you get the information from uh, the outer space, and you want to understand how to decipher it. What to make of it, what to use it. Now, there is of course a new era in astronomy which relies on uh, intercepting gravitational fields, the gravity waves through the experiments like LIGO, laser interferometric gravitational observatory, which there are two of those. One is in Louisiana, the other one is in Washington State. Those use a different kind of mechanism, but they are still relying on field theory for that, right? Gravity is a field, and there are these gravity waves that are created. Those waves are intercepted using lasers. So again, even there, even though it's a new type of window, a new way of looking at the universe, even there you need concepts from E&M because and in general, deeper concepts of fields. And so those are the things. So besides its fundamental importance, electrodynamics is of tremendous practical importance, and there are innumerable engineering applications, some of those which I alluded to you during this discussion. Okay, so that's the motivation for developing this understanding for E&M. And now, of course, you have some basic conceptual understanding, but we're going to go dig deeper. Course objective from my side is to provide you with strong foundations in the concepts and mathematical techniques of classical electromagnetism at the graduate level. So both concepts and mathematical techniques are important. Here's the rough list of topics that we will cover: electrostatics, boundary value problems in electrostatics. So here's for item 2, some of the methods that we developed for solving partial differential equations in the math methods class last semester. They will be useful here. And so if you're not familiar with those, you need to catch up. You can use Arfken, you can borrow notes from the other classmates, or I can provide some resources as well so that you can build the foundations there. Then comes the electrostatics in dielectrics, which is meaning in the presence of materials. How do materials respond to electric fields? That's a very, very difficult topic, but it's also very interesting, very useful. This is how all of the interesting things in electrostatics happen. Then, of course, in parallel, magnetostatics, and then magnetic materials, and then at the very end, electromagnetic waves, right? So, so far historically, I have only been able to write down the wave equation, but I haven't been able to go beyond that, right? So we may not reach there. Depends on how fast we are able to do things. And again, my aim is not to go fast. The aim is to make sure you follow, you understand, and you develop some sort of a comfort level with the material, so that I won't be able to cover all there is to cover in E&M. But if I give you the tools to feel comfortable and to study on your own, that is going to be more meaningful for you, meaning more useful for you. Okay, so that's the aim for me. And I still have to update the dates. That's why the syllabus is not on Western Online yet, which will happen towards the end of the day today. Let me just quickly check how these dates will shift. They normally shift by 2 days, but let me just quickly take a look at the calendar here, so I can tell you roughly right now. But we will briefly touch on that on. Okay, so they will be shifted by 4 days forward. Okay, that's going to happen because we're starting the semester about a week late this time compared to that time. So we are going to be shifting everything by 4 days. So read this as February 24th, March, that will go into April. Oh, it's 31st. No, it will be 31st. So it will still be in March. The third test will be on April 28th, and then the final would be on the 9th. Okay, so everything shifting by 4 forward. So that's good. It gives you a little bit more time, if you will. I will have the dates updated, and then it will be on Western Online. Attendance is expected, although not mandatory, meaning I don't take attendance. But if you're not there, you're going to miss out quite a bit. So try to be here always.
So the test schedule is shifted 4 days, each one?
4 days, yeah, each one, right. So it's just make sure you put those dates in your calendar once I have the updated syllabus on Western Online. That's important because you may have other tests, other things coming up. You want to set that time aside, and the test will take place during the class time. So we're not going to have extra time where we would do this. The exams will be open notes. So the stuff that you write down or the one that I provide to you, I will be writing down things just like we write on the chalkboard. But because we do this electronically, I will be providing you a PDF of that. So you don't need to be worrying about taking down notes. I will be providing whatever I write, you will have a copy of it. So you want to focus on understanding and making sure. But when it comes to math, only when you are writing things down, they will make a lot more sense for you. So you need to be practicing some of the derivations that we do in the class. Try to do those in your own time without looking at the material. That will really help you develop the framework, conceptual framework that we need. And a couple of things that I will be doing differently this time compared to the last time teaching is we may do electrostatics and magnetostatics in parallel. So we can go electric and magnetic discussion sort of parallel. So you sort of see the differences between them. We can use the similarities to move faster. So there are some similarities between them, but there are some differences. And but it helps if you go do those things in parallel. It helps to use those differences and similarities to develop deeper understanding. That's one thing that might change. We will have more focus on the conceptual understanding of things. So in your midterms and exams, there will be conceptual parts for them. So make sure you are able to express yourself clearly when you're asked conceptual questions or procedural questions as opposed to mathematical details. So in physics, here's sort of the general structure of dealing with problems, right? And so physics is a problem-solving endeavor always, even if you're not really looking at a problem per se. When a researcher works on something, they have a question in mind, and then they create a problem, right? And then to be able to answer that question, you create a problem, and then you try to solve that problem. I'm talking about the theory aspect of it. So the problem is always in a contextual sense, in plain English, something that we can express, right? Maybe not to express to a person on the street, but at least another colleague who knows some of the technical vocabulary. He will be able to understand what that question is talking about. And then you have to take the question, the contextual or the English language information, and translate that into mathematics. Believe it or not, it's a very, very difficult step, very, very difficult process. And I have seen students in our master's program struggling with that, converting the word problems or the contextual problems into a mathematical model that you can then handle. They are very good once you have that initial step, solving through the mathematics and arriving at the final answer. This part you have it down. Most of you do very well in that, but your conceptual mistakes are at the beginning and at the very end. Once you get that final equation, what does that equation really mean? That is again another very difficult part. That's these two elements: the initial part of translation of English language into mathematics, and then the final equation translating the mathematics into meaningful inferences about the world that we live in, or the universe even. Those are the most difficult process. That's what separates physics from mathematics. And so this is what you want to be focusing on. Mathematical techniques, of course, are important, but that's just a tool. It's just knowing all of you are very good at knowing your tools and using them. But there are these missing parts that we need to focus on. And so I will be doing quite a few things differently this time, so that I can test you on this and kind of give you a practice on developing those ideas. And then it just makes you a good, better physicist, because you have this tool to ask right questions and translate that information into right models. And not just that, but translate the output of your mathematical model into something that's meaningful, something that's that you can express and use in real life. Okay, so that's just the syllabus. Let's get started on some of the basic. So today we're not going to do much of a mathematics. We will do sort of a conceptual framework of ENM, some of the basic ideas that ENM is based on, and some of the conceptual jumps that you need to make in order to understand the reach of electricity and magnetism. And you can sort of see from the basic motivation that we discussed and some of the things that we talked about, ENM applies on the scales of the universe, right? That's the tool that we use, the electromagnetic fields emitted by certain objects in space is what we use to study them, to infer about them. So it's our greatest remote sensing tool. But at the same time, it is also useful, important, and relevant on extremely small time scales. The time scales of humans, right? All of us are here, and our formulation, the form that we have, the structure that we have, the tabletop on which my laptop is sitting, the structure of all of the materials that we find is governed by electromagnetic fields. Going deeper into that structure at the atomic level, electromagnetic fields are important. At the subatomic level, electromagnetic fields are important. And so because they cover a wide swath of distance scales, you need to understand when to use microscopic methods versus when to use macroscopic methods. And so that is one of the important conceptual jumps that you need. Now, in the undergraduate level ENM, you just briefly discuss that when you talk about the response of dielectric materials to the presence of electromagnetic fields, dielectric or magnetic materials. But beyond that, you don't really go into the foundations of where these things are coming from. And so we're going to try to understand that in the beginning today, and then we will start the mathematical idea. So just to kind of point out the quantum side of things is, so the fundamental particles that everything is made of and their interactions, how do they work? That understanding was developed beginning from 1960s through what we commonly call it as a standard model of particle physics. So this standard model, if you look at it from that point of view, it's now a higher level theory. So in some sense, it encompasses what classical electrodynamics is all about, because standard model includes not just the electromagnetic force, but it also deals with the nuclear strong force and the nuclear weak force. So all of these three forces are combined together. Gravity, we haven't been able to do that yet, right? So otherwise there would be a theory of everything and there would be a class teaching you about theory of everything. One other thing to be mindful of, standard model is not the last word, because again, gravity is not part of it. So there is some physics beyond standard model, and that's what high energy physicists still study, which is string theory and M theory and so on. So we're not going to go into the deeper, into those details, but we can think of electrodynamics, because standard model is sort of a higher level theory, goes much more at a fundamental level. Then classical electrodynamics should be a limit of quantum electrodynamics, which is sort of the basis of standard model. And so how do we achieve that limit? The basic idea depends on how many photons are involved. So I'm sure all of you are familiar with the concept of a photon. It's an indivisible packet of energy, and the amount of energy in a packet is given by the frequency, so h nu, right? And so the how many photons do you have accessible for your system at any given instant is what determines whether you are in the quantum domain or in the classical domain. Now, those of you who did the quantum measurement class last semester with Dr. Wong, there you had you were kind of in the mixed domain. You did have large number of photons, but they were not as large as a classical field. You would get maybe a count of 32,000 or something like that, which is a small number. But even more than that, each individual pair of photons that you were looking at, they were actually correlated. So you saw correlation between the two detectors. So that's the quantum properties of radiation. What we are going to do is not the quantum property. So we're going to assume we have extremely large number of photons, but the momentum carried by individual photon is still very, very small compared to the momentum of of the material system. So materials are going to be large. They are in some sense momentum reservoirs, and then so we're not going to see any mechanical effects in this class of light falling on materials. There's actually a little demo that you can build. You can build a fan that's sitting on a pin top, right, a top of a pin, which has, let's say, four vertical, 4 or 3 doesn't matter, 4 vertical thin sheets of aluminum, which have colored on one side with a dark color, and then you shine a flash lamp on it. You will see a mechanical effect. You will see things. It will start rotating because it's sitting on an axis there. And so there are mechanical effects of light. There is a talk of building solar cells using the solar radiation to transport a spacecraft across space, take it away from the solar system, and to see if that would give you any advantage in terms of speed and such. So there are mechanical effects of light, right? So we're not going there. We're only looking at a limit where you have large number of photons, but each photon carries extremely small momentum. Okay, so just to kind of give you an example, let's take a frequency of a photon about 10 to the 8 hertz. If you calculate this, so let's see, what I will do now is share my screen with you. Okay, so you can see this. This is how I would be writing down. That's my whiteboard, and you will get a copy of this. So let me just kind of set the stage for things that we're going to talk about. Okay, so that's our topic for the rest of the discussion today. And what we saw is ENM, or rather classical ENM is a limit of quantum electrodynamics And in the limit of what, right? That's important. So large photon numbers and the second limit is individual photon momentum small. Okay. Anybody remembers how to calculate the momentum of a photon if you know the frequency? What's the momentum of a photon? Anybody?
hc by lambda.
hc by lambda.
H by lambda. Okay, very good.
hc
Is it H over lambda or is it H bar over lambda? Does anybody remember?
hc by lambda or h by lambda.
Yeah, what is I'm asking you. Do you remember?
It's h bar by lambda, I guess.
H bar by lambda?
H by
Yes,
lambda.
anybody? Yeah, Al-Masud, did you say something?
H by lambda.
H by lambda. Okay, and then, but I want to write this down in terms of the wavelength. So how would it, no, in terms of the frequency. So how would we do that? Anybody? New? Right, everybody agrees? Because C, the speed is nu lambda. Then, and C is the speed of light. So that's how you get the momentum. Now let's see if this makes sense, right? H is extremely small. H is of the order of 10 to the negative 34. Nu is going to be of the order of 10 to the 8 hertz for now. We're going to take it to be that. The frequency of the visible light is kind of in that range, several gigahertz. This is actually smaller on the smaller scale, about 0.1 gigahertz. So it's about 0.1 gigahertz. Right? Giga is 10 to the 9. So one factor smaller. And C is 10 to the 8 meters per second. Is that correct? What is the speed of light? Anybody remembers?
3 tenths in the eighth.
3 times 10 to the 8 meters per second, right? So I'm just doing the order of magnitude, so 10 to the 8. So you can see nu and C, they more or less cancel. And so the momentum is roughly of the order of h, right? And so very, very small. That's the individual photon momentum. Okay, and that number actually, if you wanted to talk about this, so when the photon hits an object, it's going to impart its momentum. So it's essentially equivalent to giving an impulse, and so this leads to an impulse of the order of about 2.2. Now this here I have done all the detailed calculations, but the idea was that it's 10 to the negative 34. That's important. Newton second. So, almost negligible. And even if you have millions of photons coming in, still overall effect of the momentum imparted, it's going to be negligible, right? So that is important for classical electrodynamics. That means, what does this mean? Impulse is that small. That means no mechanical effect of light or electromagnetic field on materials. So what sort of effects are we looking at, right? So we need to be very, very careful when you're building your models to know what the limitations are. We're not going to study mechanical effects. If you want to study those, for example, in quantum optics, there is a very, very famous work that was given Nobel Prize in physics in 1997, just the year I actually started graduate school. That was for laser cooling. So even though it's happening at the quantum level, you are intercepting the quantum degrees of freedom, the discrete energies of an atom, and shining laser light with them, there is a mechanical effect there. And that means you need to now bring in different sort of that effect becomes important when you have large number of photons, so lasers, but not a bulk material. The material is now single atoms, right? So, or very small number of atoms, about 1 million atoms in a cloud. You shine laser on it, and the way they do this is there are lasers coming from 6 different directions: up, down. So there's a laser coming from up, there's another one coming from down, and the cloud is somewhere in between in vacuum. Then you have one coming from negative x, positive z, negative z, and positive y, negative y, right? So you have lasers coming in all 3 independent coordinate directions, and the laser is tuned slightly below resonance, right? So normally what happens is you know something called resonance. If you want atom to interact and provide you something interesting, you have atom here, the electrons there, you apply a laser field, it generates essentially a dipole moment, meaning it causes some of these atoms to go up. And actually what happens is, in the presence of electric field, if the frequency of the electric field matches the energy level difference between the energy of the photon matches the energy level difference between the 2 levels, then you just have absorption, and the atom will go get excited and will come back down. There is an oscillation going on between the lower level and the upper level, right? And so if you look at the population of the upper level, with time, you get, let me do one more thing here. Okay, so that's a 0 level, if you will. And so what you get is population oscillations. So between 0 and 1, so it just oscillates. So that's boring, that when you want to do laser cooling, that doesn't tell you much. What is interesting is if you now detune the laser, so instead of being exactly on resonance, there's a slight bit of the frequency difference. So the laser frequency is slightly smaller than the atomic frequency, which is the energy difference divided by h bar, let's say. In that case, what happens is the atom, if it is moving towards the laser, it gets Doppler shifted. Remember Doppler shift? And then it gets into resonance with the atom, and then it gets a kick from the atom. And so then the momentum kicks start becoming important. So in this case, velocity dependent momentum kicks. Imparted by the photons, by the laser. If the atom happens to be moving in the opposite direction, then the laser in that opposite direction will give it a kick. Going up, the one coming down, that's going to give it a kick. So it just, they all basically kick the atoms, and eventually they just coagulate in one small space, and that's laser cooling. And if you increase the density sufficiently large, then and if you have bosonic atoms to begin with, then you create a Bose-degenerate system. Bose-Einstein condensate is what it's called. Or you can even create Fermi condensate if you start with the fermions to begin with. But of course, because of the Pauli exclusion principle, the Fermi condensate are much larger in size compared to the boson. So that's just one example of mechanical effect of light being important at the quantum level, right? So again, there are always exceptions and some interesting situations to study, but that's important to kind of understand. Okay, so what are we doing when we are looking at electromagnetic fields? In the quantum domain, so let's take a look at what's the difference between the classical and the quantum domain. In the quantum domain, So that means you have small number of photons. We need to take into account both the quantum nature of the atoms, meaning the energy levels are discrete, and the light field. In the quantum domain, both atoms or material and radiation is quantum. And so an example of that is the spontaneous emission of radiation by atoms. So if you excite atoms by certain means, so in certain laser systems, you use electricity to excite atoms to upper energy levels. And when they come down, they don't like to stay in those upper energy states because they're not very stable there. They come down and emit radiation. So that's spontaneous emission. You just leave them there. If you want to manipulate that, if you want all of the photons coming out to be coherent, meaning them all moving in the same direction, have exactly the same frequency, then you need something called stimulated emission, and that's what Einstein sort of did that. So even in this case, actually, there is a semi-classical theory. You don't always have to treat everything quantum. And in that semi-classical theory, light is just classical field. But atoms are quantum. And most of the quantum optics that I talked about actually does this. The optics that you did in your quantum measurement class, there's not much, not many atoms there. You don't worry about the nonlinear process that is going on in the source. It just gives you this entangled photonic source, and you're trying to analyze that. Their light is quantum because it's shows these very interesting sort of quantum properties or entanglement properties. Another interesting thing to recall and remember is the electronic charge. You can't ignore the electronic charge when you're studying electromagnetic radiation. Electrons and their motion, even though we're ignoring mechanical effects, electronic motion is what's responsible for a generation of electromagnetic waves. So electronic charge, is it continuous or discrete? Anybody? You know this very well. QE magnitude is 1.6 O2 times 10 to the negative 19 coulombs. So it is so small, right? It's very small that even though the electronic charge is discrete, when you go to quantum electrodynamics, you can't avoid the discreteness of the electronic charge. For example, when they build these superconducting circuits for, even for quantum information application or for study of superconductivity and such, you have a barrier along which the electrons jump, and you can literally count how many electrons have jumped. So you can, the electric current becomes quantized when you go into the quantum electrodynamic domain. You don't have continuous current. You can't think of electronic flow as continuous. You can actually count the electrons jumping. So in that domain, but here, so the electronic charge is discrete. That means the total charge on any material has to be some integer number of the electronic charge, where n is an integer. Right? This is strictly speaking true, but in classical electrodynamics, we worry about macroscopic materials. In classical ENM. That's going to be the short form that I would use. And so we can assume, we can safely assume charge to be continuous, or let's say charge distributions to be continuous. So at the back of your mind, you need to remember charges are discrete, but the theory is going to ignore that, right? And so this leads you to have the charge density, for example, as a continuous field, essentially in a given medium, and the current density, electric current density, both of these quantities are continuous functions of the position coordinate r, right? The position vector r. Okay, and so r is a 3D position vector of a point in space. Does that make sense? Everybody with me? Okay, so those are kinds of assumptions that you need to be very, very mindful of. Okay, for the electrostatics, our foundation is the Coulomb's law. Is the Coulomb law. And again, this is important time to remember that physics is an experimental science. The very first input in any of the physical theory has to come from experiment. It's something that you have learned experimentally or through observations, and you take that and then you start building models based on that. So Coulomb's law is an experimental reality, right? It has been measured many times, and we know it to be true. It is also important that it's true over, I shouldn't say true, I should say verified or hold over at least (25) orders of magnitude in length scale. Right. And so what we have basically, let's just write it down. The Coulomb force is some constant K, which we will write later. It's Q2 charges, Q and Q2 over R magnitude squared. Okay, R is the distance between the two. Let's call it R12. That's the distance between the two. And that's, of course, going to be a vector, but you just care about the magnitude. So this 2 could have been something else. It could have been 2 plus an epsilon. And if you want to verify Coulomb's law, you're trying to find the upper bound on that epsilon. What's the largest value that epsilon can take, right? And so it is extremely, extremely small, very, very small number. And that's what you would do if you figured out a very precise measurement technique for forces. This is something that you could try to check, right? Because the whole ENM theory is based on that. That's the foundation. We take Coulomb's law to be granted, to be given, and then we go from there. Same thing with Newton's law, right? They are the experimental observations turned into specific statements. Same thing applies to Newton's law of gravitation. Those are experimental observations, experimental reality, and then that becomes the foundation for the later part of the theory. And you, of course, know how successful Newton's law is, right? We're able to throw a dart 250 miles above the Earth's surface and dock it with the International Space Station. And so those are the successes of the confidence that we have, even though we know for sure it's not the final word, right? Einstein's theory tells you that there are departures from Newton's law of gravitation, but for the most of the things that we do, even the James Webb Space Telescope that is being put on the orbit at the L2 point, Lagrange point. We will learn about Lagrange points in the next class, classical mechanics, those of you who haven't taken it with me. There, all of that dynamics, when you need the burns for the spacecraft to get on the right path to reach there, all of that can be done using Newton's laws. You don't need to use Einstein's gravity there. Only for time correlations part, you need the Einstein's general theory of relativity. Okay, then okay, so what we are going to do in E&M, another important process is that the Maxwell's equations, which you are all familiar with, you have heard about them, but we will take a look at them in detail. They are second order partial differential equations. And if you know a little bit about what we did in the last class, in vacuum, because there are no material response terms coming into the picture. So in that case, the Maxwell's equations are essentially three-dimensional partial differential equations that are linear, right? So, and in the fields E and B or H, we will use these B and H interchangeably for now, but then later on I'm going to stick with from next class onwards, I'm going to stick with Zangel's convention, and then we will be using only one of those to not confuse, right? There are different practices that are followed by engineers versus physicists, and so to mix things up, we need to be consistent, and we will be consistent once I introduce the symbols and the meaning next time, the precise meaning. Okay, so if that's linear, there are situations where you depart from linearity, in which case, if you have materials, like for example, the first box in your quantum measurement experiments, that box had some material, a special crystal inside, where when you shine laser on it, it generates non-linearities, and it's able to change the wavelength or the frequency of the incoming radiation into it turns it into half, I think, yeah. And then it generates 2 photons of half the frequency. And so there is that process cannot be described by any sort of a linear process. It is linearity. So non-linearities are material dependent, and that comes under the purview of a field of nonlinear optics. So we're not going to deal with nonlinear optics here. We're going to be basically doing linear processes. Any questions at this point so far? No questions? Okay, so now let's take a look at further details on idealizations. And these will commonly we will encounter them very commonly in some of the problems or the situations that we deal with. For example, surface distribution. Let me put again an itemized list here. So a surface distribution of charges and currents. This is idealization. Doesn't exist in real world. You don't have a single thin no length layer where you have the charges. There's always going to be some special extent, right? It's going to be always distributed. For example, the charges that exist on a surface of, let's say, a sphere, is not just on the top atomic layer. There would be multiple atomic layers where you would have that charge spread out, but we ignore the thickness, right? So we take NENM, we take the limit of the thickness going to 0. Okay, so that's idealization. You can be pretty precise about doing those calculations, as we will be in the case of when we look at some of those problems. That's a nice thing about Zangwill's book, because he doesn't leave these kinds of things that just idealization. He goes deeper into it, and he will rigorously show you mathematically how it makes sense. So normally in mathematics, you may encounter these kinds of limits where thickness is 0, or some quantity suddenly becomes infinite. Thus, these kinds of things do not exist in the physical world. There is no such thing. So that's why, if you know, one very prominent example of infinities cropping up into physics is black holes. You have a finite mass in a 0 volume, which is going to mean you're going to have object with infinite density. That is still perplexing to us. We don't understand it. So I will still stick with the statement that these infinities do not exist in the physical world. So we don't quite understand fully how the black holes work, right? And so it's still an open problem, if you will. Everything in the physical world happens over a certain distance scales. It has certain finite size to it. So object with size 0, that's the perplexity with black holes. And then another idealization, holding an object at a fixed potential with respect to some 0, right? You always need the origin or the reference point for the potential. And the 0 is called ground. This is another idealization in ENM. It doesn't exist in the real physical world. It's very difficult to keep something at a fixed potential. There will be fluctuations and so on, but we ignore those fluctuations for most part, because if you get trapped into those fluctuations, it would be very difficult to calculate anything. So how do we do that? To hold the object at some fixed potential, you need to have from time to time a conducting path or its equivalent from that object to some source of charge that's far away. So to hold the object at certain fixed potential, it needs to have certain amount of charge on it. And so that means that charge is if you just leave it in space like that, especially in humid times, summertime, for example, that charge will leak away very quickly. And so that means to be able to hold that object at that fixed potential, you need to provide a source of charge. It needs to be connected with something that will replenish that charge every so often, just precisely. And so then, you can then maintain the potential. So this is a difficult thing to do in practice. Okay. And another thing is kind of looking at the effect of these conducting wires that are connecting this surface to be kept at specific potential to a source of charge. You want the wires to be as thin as possible, which is, of course, essentially limiting to the thickness of 0. Again, that's idealization. You can't do that in practice. The reason being, when these current carrying wires or the charge carrying wires carry charges, they are going to alter the electric field in that region, right? So there is, again, very small effects that can occur if you're not careful. So that is what is important. Let's talk about the concept of grounding. And so, a next step from that is the concept of grounding. By keeping an object grounded, meaning at potential, let's say V equal to 0, to be able to do that, it's not just sitting in space somewhere. It has to be connected to a extremely large, right? So it requires electrical connection to an extremely large charge reservoir. Meaning, the amount of charge of that reservoir is not going to change very much. And so we take the earth to be the reservoir. So that's why the electrical appliances in the house have to be grounded, meaning there has to be a connection somewhere in your electrical system in the house to the ground. They actually literally put a wire in the ground and make sure it's connecting well. And there's sort of process where they use salt and stuff to sort of achieve that. So the idea of grounding something, again, is a very important concept in electrostatics. And you need, for electrical systems to work, you need to have a good ground. So that's kind of important. Let's take a look at now a couple of ideas for these surface. Yes, somebody had a question.
Yeah, it's me, Khaled.
Yeah, go ahead.
Yeah, doctor, he said that connected to an extremely large charge reservoir, right?
Mm-hmm.
So we, from previous knowledge, that we know that, I mean, as we remember that Earth is neutral, right? Or
Yes.
isn't?
Well, you can't say that for sure, right? It's an extremely large system, and overall it may be neutral, but it has ways to absorb inordinately large amount of charge, right? So at least the charges that we encounter in our everyday life, in the electrical appliances and such, it is able to absorb those. It's able to conduct those. Maybe it's not staying on the surface, because if it was a fully conducting surface, then the charge would stay on the sphere. So there's going to be regions where you will have large amount of charges. So if something is neutral, does not mean it has no charges in it, right? It's just that the overall positive and negative charges balance out. But it can also act as a reservoir, meaning the total amount of charge doesn't change. It is able to absorb a large amount of charge, and it doesn't stay on the surface. So you won't get electrocuted essentially, but it's able to absorb charges by you have ionic solution. The earth has lots of water, and the water is almost always not in a pure form. There are some salts that are dissolved in it, and those dissolved salts will carry away free charges. And so there is a mechanism by which you can do that, right? So I think this is a good point, good place to stop. We will deal with a couple of interesting mathematical functions to help you deal with these idealizations of, let's say, the surface distribution of charges and such. How do we handle them? If they are these idealized formulations, you still need some mathematical machinery to be able to deal with them. That's what we're going to do in the next class. So thank you very much for joining. Your class webpage will be up by the end of the day today with the syllabus and today's notes up on there.